Hello, welcome to today's maths video where we're looking at a brand new topic called numerical methods, which we're going to be using to help us solve equations. And the reason we're going to be doing that is that sometimes when trying to solve equations, such as the one you can see on the screen right now, you encounter a problem, which is that this equation, for instance, is one that's not possible to solve analytically using the elementary functions. What we mean by that is that effectively you can't solve this equation by using algebra rearrangement, no matter how hard you try, just by using the functions you've already come across before in Maths A-level. And that's pretty unsatisfying, particularly as if you look at the graphs of these two things, you know they do intersect, so therefore there must be a solution, it's just that we can't find it. So this is where numerical methods come in, because numerical methods are a way of being able to estimate an answer to a mathematical problem rather than using algebra rearrangement. And the other advantage of them is they're an easy thing you can code a computer to do so that the computer can just very quickly compute the answer for you. So super important and useful in the modern world. To help illustrate what a numerical method actually is, we could start with the most primitive form of them, which is to start with something that could effectively be viewed as guesswork. We could basically take a bunch of x values and plug them into the equation and then see, almost by guesswork, whether they actually solve the equation or not. This wouldn't be a problem if you're using a computer, because a computer could type in lots of different numbers in a very short time. Not such a good method if you're doing it manually, but there you go. So for instance, we could plug the x values -1 all the way through to 3 into our equation, both sides of it. And if we do that, these are the values you'll get. You'll notice that for x equals -1, 0 and 1, the values of e to the power of x are bigger than the values of x to the power of 5, which means if you're looking at the graph, the y values of e to the x are above the y values of x to the power of 5. But then, from x equals 2 onwards, we notice that things have changed, because now it's the y values of x to the power of 5 that are bigger than the values of e to the power of x. That means we know these two graphs must intersect somewhere in between 1 and 2, because if a graph has gone from being below to being above, then that means probably the graphs intersect somewhere in between there. However, temporarily putting aside the most obvious criticism that I can probably guess that a lot of you are already thinking of, another problem with this method is that as you start to look at more and more decimals, it becomes more and more of a pain for a human to try and spot where the root is. For instance, if we look at these decimals, there is a root somewhere in between these decimals, but it becomes more and more of a pain to check where one y value starts becoming bigger than the other. So, therefore, there is an adjustment we can make to this method that will keep it still very similar, but just a bit easier to do. And it's called the change of sign method. For a start, your equation needs to be in the correct form. You need to rearrange the equation so that it's equal to 0. The advantage of this straight away is it means that we're now not having to plug x values into two separate things and compare the y values of those two things. We're only plugging x's into one side of the equation, and the right hand side of the equation is always staying at 0. And this adds another layer of convenience, because if one of your graphs is y equals 0, which is of course just the x-axis, and then the other graph is crossing it, to know when it's crossing it, you're basically noticing when the y values have gone from being negative to being positive, or vice versa. Which is great because it means you don't have to look at the entire number to know that this situation has happened. You literally just need to look at the sign in front of the number and see has it gone from positive to negative or negative to positive. So repeating the same process we had before with this same equation, but now in a way that will make it a lot easier to spot, we can have those same decimals we had before, but now plugged into x to the power of 5 minus e to the x, and we can see straight away there's been a change of sign here, so therefore that means we know the root lies in between these two decimals. A lot quicker and easier to spot, and less things to compare. Nice, and ultimately that is the main idea behind this method. It just boils down to this idea of plugging numbers into your equation and then looking out for a change of sign in the results to know the rough location of a root. And that is ultimately one of the main advantages of this method, its simplicity. It's really easy to carry out, and therefore it's very easy to program a computer to do with very little effort indeed. However, we can't avoid it any longer. This method does have some big flaws, so let's take a look at those now. One of the first ones is the most obvious one, which is that this method takes far too long to be able to find a root to a high level of accuracy, because you have to plug so many different numbers in to eventually narrow down to the level of accuracy you want. One way around this though is the fact that we don't actually ever tend to use this method to find the full root in the real world, and instead this method is often just used to give you a starting point to know roughly where to begin looking for the root. But therefore we encounter some other issues instead, namely that sometimes although we're looking out for a change in sign to tell us if there's any roots or not, that won't always be enough. Because for instance, we might sometimes have a couple of y-coordinates for which there are no change of sign in between. So for instance, we could have this point here and this point here, and there is no change in sign because both of these points have a positive y value. But that doesn't mean that there are no roots in between these two values, because the graph could be doing something like this. Because the graph started above the x-axis, then dipped below it, and then went back above it again, we can't see just by looking at our particular two y values that there is a root in between these 2 points, and therefore we might miss out on finding or even knowing these roots exist if we're just using this numerical method. Alternatively, you can have issues, of course, with points having repeated roots, which is a situation where a graph has a stationary point on the x-axis. And not only is this a problem, there's also some other issues we need to watch out for, such as we need to check that the graph is continuous in the interval in which we're checking for a root. A way of explaining what this means is to say that you should be able to, in the interval you're looking at, be able to draw the graph by starting at the first point in the interval and connecting it up to the second point in the interval without taking your pen off the paper. In other words, the graph continues between those 2 points uninterrupted. Therefore, that means you do need to be watching out for points on the graph where there are vertical asymptotes or just x values that you aren't able to plug into the graph, because that is an example of where a graph is not continuous. These are called officially discontinuities. The reason this is important is because you might, for instance, have a point that's above the x-axis, in other words, has a positive y value, and you might have another point that's below the x-axis, in other words, has a negative y value. And the reason it's important that the graph is continuous is that otherwise the graph can effectively cheat. Although you can see a change in sign, the graph is able to get from above to below the x-axis by magically jumping there. For instance, this graph could be one of the ones with a vertical asymptote, so it could be appearing like it's going up, and then magically it's all the way down here, and then doing this instead. So we've managed to go from a positive y value to a negative y value without ever actually crossing the x-axis, therefore without ever actually having a root. But even after we've checked for this important condition, there is something else we need to be aware of, which is that you need to know that a change of sign indicates at least one root in the interval. And the reason for that is, of course, if you've got a point above or below and another point that's the other side of the x-axis, you could have the graph going up and down multiple times before it reaches your point, to the point where it's got multiple roots in that interval. So that's something to be aware of in your language. So now that we've done all that explanation, we can now get on with an example. So we've got to show that a root to the equation 3x equals tan x lies in the interval 1.32 to 1.33, and we're also given that x is in radians, which is of course important because we've got a trig function. We've got to make sure our calculator is in radians mode. So first thing we've got to do is be aware that the change of sign method only works if the equation's rearranged to be equal to 0 first. So that's what I'm going to do by simply taking away tan of x from both sides of the equation. And then all I've got to do is plug in, first of all, the first value that's in the interval, which is 1.32. So at x equals 1.32, we've got 3 lots of x, so that's 3 lots of 1.32, minus tan of 1.32, and that will get you an answer of 0.0567 to 3 significant figures. Cool. And then we're also going to plug in at x equals 1.33. So if we do that, we get 3 lots of 1.33 minus tan of 1.33. And if you do that, you'll get minus 0.0823 to 3 significant figures. And what do you know, when we look at our two values, there has been a change in sign because the first value was positive and the second value we got as an output was a negative value. So therefore, we need to be aware that this is a show that question, which means we now need to write a conclusion to illustrate that we're aware of what's going on and why that means there is a root. So here are the things you would need to include in the conclusion to guarantee you get the marks. You need some sort of mention that the change of sign has occurred. So therefore I'm going to write, therefore, as there has been a change of sign, another important thing we need to include in our conclusion is mention of the fact that the graph is continuous in the interval. That's a particularly interesting point in this example because the graph of tan of x as a whole isn't actually continuous for every value, but just between our x values of 1.32 all the way over to 1.33, tan of x has no asymptote, so just for that little portion, it is continuous. Therefore, the conclusion that we're making is that there is at least one root in the interval. It helps also to note what the numbers in the interval are in your conclusion. It's always helpful in all wordy things in maths to be specific in your answer. Although vague statements might technically be true, they will not often get you the mark because you haven't demonstrated enough with what you've said that you know what's going on. So that's why I've included the actual numbers of the interval in my conclusion as well. So there you go, that's something to be aware of. Let's take a look at another example that makes use of change of sign in order for you to be able to prove or show that there is a root in an interval. So they might word it slightly differently. This time they've given us the function and we're trying to solve the function f of x equals 0. So it's already in the format we need for change of sign because it's already been rearranged to be an equation equal to 0. They've also used function notation, which will make it easier to demonstrate what it is we're doing when we're writing it down. But they tell us by considering a suitable interval, show that the root is 2.274 3 decimal places. Now, because they've used the words by considering a suitable interval, that's what gives you the clue that it's a change of sign question. But what is the interval? Last question we had, they gave us what the numbers for the interval were going to be, whereas this time it's rather open-ended and instead we're just told what we need to show the root is. But that value for the root is itself going to give us the clue as to what the interval's got to be. What you want to do is you want to choose an interval so that every single number in your interval is guaranteed to round to 2.274. That way, if it lies in the interval, the root must be the number 2.274 rounded to 3 decimal places, which is what the question is asking us to do. So therefore, if we call our root alpha, then we know that alpha must be between 2.2735, because starting that number and going up, numbers start to round to 2.274, all the way until we get to 2.2745, but not including that number technically because that's when the numbers start to round to 3 decimal places to 2.275. Cool. In interval notation, by the way, that would be writing it like this instead. Remember, it's a square bracket if it's including the number, and it's a normal curved bracket if it's not including the number. So just showing you the two different notations there. Anyway, we now have the values we need to do our change of sign with, so that's what we're going to do. So first of all, plugging 2.2735 and making use of function notation to show this stuff. So therefore, we plug that in and we get, in this case, minus 7.75 times 10 to the power minus 3 to 3 significant figures. And then we also plug in 2.2745 into our interval. And that comes to this, to 3 significant figures. And what do you know? There's been a change in sign, so therefore, as this is a show that question, we now just have to do a conclusion to illustrate that we know what's going on. So therefore, basically very similar to the previous example, I'm going to say, as there has been a change in sign, in our interval, and the function is continuous, because neither of those two parts of this graph are ones that have vertical asymptotes or discontinuities. Therefore, we know the root lies between 2.2735 and 2.2745, so it must round to 2.274 to 3 significant figures. Sorry, I'm cramming that in at the bottom at the end. And there you go, that is how the change in sign method can be used to help show that a root lies in a particular interval for an equation. If you do any further research, you'll notice that there are a few other methods that utilize a similar idea as this one to help you find where a root is, but for Maths A-level, the change in sign method is the only one of this very specific style of numerical method that you need to know. But there are other numerical methods that we need to know to help us solve equations, and hopefully they'll be better than this one, right? Well, stay tuned because we'll look at those in some future videos. Goodbye!